Now let's try to do something better. So I don't know how well you remember the quantum teleportation protocol we started out with. But, Alice, what did she do? She took her quantum state and threw it into a machine, and it did some measurement. She got this answer 3. So she did some kind of a measurement on the system, got the answer 3. So you should try that here. So she starts the same way, throws the quantum state into the black hole. A little while later, she does a measurement. She does a measurement here. What she does, just measures a piece of Hawking radiation. If you don't know what Hawking radiation is, that's okay. It's just a little bit of radiation coming out of the black hole. She has a detector where she's able to capture one piece of Hawking radiation, measure it. She measures it at this later time. And what that measurement does, measurements in quantum mechanics are a somewhat violent process. What it does is it creates a little bit of positive energy that propagates into the black hole. She's now thrown 2 things into the black hole. That seemed to help very much. She threw her quantum state in, and she measured a piece of Hawking radiation later. They threw in a little bit of positive energy. Okay, that's what's happened so far. The final step in quantum teleportation is that Alice needs to tell the answer of her measurement to Bob. So she needs to say the number 3 over the phone to Bob. So let's assume Bob at this time knows that the answer to the measurement was, let's say, 3. So Alice measured some piece of Hawking quantum. She got an answer, tells it to Bob. Bob now knows the answer was, he doesn't have the quantum state. He knows the result of the measurement on this piece of Hawking radiation. What does Bob do? He acts with a simple operation on his black hole that depends on the number 3. He can act with a simple operation that depends on the result of Alice's measurement. And what that can do is it can send in the black hole a little small amount of negative energy. The reason that this is possible is that normally you can't easily create negative energy. But Alice and Bob are working together here. So Alice measures something over here. She creates some positive energy. She kind of makes a mess by doing a measurement. Bob can use the knowledge of the outcome of that measurement to clean up a vacuum fluctuation which would have existed over here, contributing positive energy. You can clean that up, remove it, and you're left with negative energy. I don't know if that makes sense. Don't worry about it too much if it doesn't. Point is that Bob can use the result of Alice's measurement to create a small amount of negative energy falling to the black hole. Yeah.
How does Alice communicate the number 3 to Bob in the server?
Okay, good. So how do they do that? Well,
Cell phone.
yeah, cell phone. So exactly. So Alice has a phone. She calls Bob. So let's assume that the black holes are not extremely far away from each other, and Alice can communicate the result to Bob. That's one answer. That's one way that this protocol could actually be carried out. Okay. The point is that there are multiple connections. Let me leave it at that. I can answer more later. Okay, we're almost done. So we're completely done. If we observe the following thing. There's a famous effect in general relativity, follows from Einstein's equations, which is called the Shapiro time delay. What it says is that if you send a light ray through a region with matter in it, the light ray will be delayed in its trajectory. So I shoot a laser in some direction to a friend somewhere far away. It will receive that laser light a little bit later if there's matter in the way. Not because the light gets blocked, but because the space-time gets a little bit curved by the matter, and that curvature delays the propagation of light ray. This is called the Shapiro time delay. Positive matter density curves the space-time a little bit in such a way that light rays are delayed in propagation. What happened here? Bob threw in a little bit of negative energy. Negative energy works the opposite way in Shapiro time delay. It becomes a Shapiro time advance. If I'm shooting a laser somewhere, you could somehow arrange to have some negative energy situated between me and you. The laser light would get there a little bit faster than it would have without the matter in between. So we can illustrate that in this diagram by saying that what happens is the new trajectory of this quantum particle has a time advance. And the trajectory with the time advance looks like this. As it crosses this negative energy, it looks like it goes backwards in time a little bit, so it goes back downwards, or downwards is backwards in time. So the trajectory of the light, or of the quantum state that Alice sent in, is now this one. And well, it happens, Bob receives it. So Bob receives the quantum state on his side of the black hole. So this operation of Alice making a measurement here, communicating the result to Bob, and Bob doing an operation, is able to make it possible to traverse this wormhole. Makes it a traversable wormhole. And that is space-time's way of accomplishing quantum teleportation. Quantum teleportation is this purely quantum mechanical thing discovered in the 90s by people who studied quantum computation, quantum information theory. And here are a pair of entangled black holes carrying out that protocol using the rules of space-time. You don't really even need to know quantum mechanics. You just need to know the rules of space-time to understand the implementation of quantum teleportation by black holes. Okay, there's a question there, but I just want to finish now, and then I'm happy to answer other questions. So thanks very much.
If Bob threw in any other number other than 3, how would the result of that the direction of the
Right. So if Bob doesn't know the outcome here, he just picks some other thing, then he's not able to send negative energy. Not able to send negative energy. It's like he doesn't know what vacuum fluctuation exists, so he's not able to kind of remove it. So if he doesn't know, then he's not able to send negative energy, and this protocol doesn't work. So in fact, without the communication between Alice and Bob, there's absolutely nothing Bob can do to send negative energy into the black hole. It's absolutely essential for him to have this information in order to do that.
Yeah, okay, so that
Yeah, maybe.
maybe in comfort. I think I understand everything you're saying, but I'm a lawyer, so I'm not my thing, but what is what does this tell us in lay terms?
Yeah.
What I get it all.
Okay.
What is it?
Okay, good. So 2 answers. First is, what this tells us is it's an example of connection, but of this absurd equivalence that I showed. This absurd equivalence between interacting system of particles and space-time theories involving black holes. And this is just one way of understanding an example of that. So if that is true, anything quantum mechanical systems can do, black holes ought to be able to do. And so here we're seeing an example, quantum teleportation. That is something quantum mechanical systems can do. It's kind of non-trivial. Here we're showing you how the black hole does it. That's one answer. Second answer is that often when you try to ask a black hole to do a thing a quantum mechanical system does, it does it in a way that surprises you. It does it in a kind of some insight to the problem. So the fact that the message goes through the wormhole adds a layer of understanding to quantum teleportation that did not previously exist. So there are 2 applications of that. So we had 2 answers to the question. Now, the second answer has 2 parts. So the first application of that is, consider the following kind of crazy philosophical idea. What does it feel like to be teleported?
Star Trek.
Okay, but well, did they know that they were talking about the right answer? So what does it actually mean if somebody does quantum teleportation to you? And the normal quantum teleportation protocol doesn't really answer that question. Here we can answer the question. The question because we can follow the trajectory of the quantum state, and what it feels like in space-time, it just feels like inertial motion. It's like it's falling. The particle just feels like it's falling in essentially empty space-time from one side to the other. Okay, so it gives you more insight into the experience of being teleported in a more practical sense. So people have used this quantum teleportation protocol to design experiments that have actually been carried out on sort of noisy current quantum computers. This is an interesting quantum mechanical effect that the black hole told us about. The black hole picture helps us to understand that experimentalists can go back and try to understand better in an ordinary quantum system like a quantum computer. So it's an example of this kind of like ping pong ball bouncing back and forth between quantum systems and space-time, where every time it goes back and forth, both peers understand the game a little bit better. That's my answer.
Okay, then in the second row.
I'm wondering if you have perhaps any friends in condensed matter physics that might have shared with you what more, if anything, we know about the state of matter inside a black hole.
Oh, well, depends where you are inside the black hole. Let's look at this picture here. Here we have a picture of space-time of a black hole, and this whole shaded region is inside the black hole. This is inside the black hole, and here, sort of barely inside the black hole. If it's a big enough black hole, things are basically the same. So you might not even notice that you're inside a black hole. Right?
Yeah, ordinary particles.
Ordinary particles, same rules of physics. If you could do an experiment, if it's a big enough black hole, you could design any experiment. You could do here, you could do it there, get exactly the same result. That changes as you get closer to the singularity. The singularity, space-time ends, and as you get close to the singularity, our currently understood rules of physics break down. We don't know exactly what happens there. Can't answer your question. And at the current moment, nobody can answer your question. At this point, everything looks normal.
But at that point, you're not getting that anymore. You're experimenting there, but your answer isn't getting back to us. Because
Right. Yeah. So you might know the result, but you can't tell it. Can't tell anybody on the outside. Though that can be subtle, because look at this diagram. This red line entered into this shaded region. They thought they was a mistake, but if they'd been a person, they would have thought at this point, oh no, like I know about the space-time geometry, I have my like space-time map with me or whatever. I know that I'm behind the horizon of a black hole, I'm going to hit the singularity. But Bob can use this information to send in some negative energy and rescue them. So it's not always it's kind of an exception to the rule that you always hit the singularity across the horizon. You can in some cases be rescued.
So Hawking radiation emitted from something close to the event horizon?
Yes.
So Hawking radiation is the appearance of a virtual particle outside the event horizon?
Oh, it's the appearance of a real particle outside. So that
Well, that happens at the borderline that you're talking.
yeah, it happens here. So there's vacuum fluctuations here, and they propagate this way. And this one comes out and becomes a real particle, and this one falls in, hits the singularity. That's the process of Hawking radiation.
Back? Yeah.
Two questions. Are you saying that what Alice did to perturb the energy and what Bob did they have to be simultaneous, or did they affect that in forever?
Good question. They have to be close in time, but not exactly simultaneous.
Okay.
Because the information that Alice gets by doing this measurement here, it's kind of only useful for a little while over here. It tells you about the vacuum fluctuations that exist only for a little while.
So she has to get the wave function in there quickly too, otherwise she'll miss that window.
Yeah, she needs to tell Bob the answer pretty soon. It doesn't have to be simultaneous. So if we had two black holes in the same universe, we could do a measurement and then tell Bob a little later. Maybe a lot later, but a little later, and it would work.